When I wrote this program a couple of years ago, batteries were kind of this mysterious market, and most solar arrays at the time did not involve batteries. What we're seeing right now is almost the solar market coming full circle back to its origins, where solar used to always have a battery associated with it for powering off grid remote applications. The problem with batteries is that they are very expensive, and solar is very expensive. And you combine the two, and you have something that is all the more very expensive. And so when solar started to ramp up in the early 2000s and the cost came down, one of the ways to reduce the system cost was to eliminate the batteries and essentially use the electric grid itself as a battery. What's interesting about batteries is they're given a nominal voltage. So you're used to thinking of a 12-volt battery, or a 24-volt battery system, or a 48-volt battery system. These are just nicknames for the batteries. For example, a 48-volt battery system can be overcharged and is often operating at maybe 53 volts at a full state of charge, and has a maximum charge of maybe 60 volts. Similarly, the electric grid can be overcharged in the sense that a solar array will increase its voltage beyond what the voltage of the electric grid is in order to push its power back onto the grid. And we've used net metering policies to compensate the homeowners for that outflow. However, if we're just thinking about batteries as a way to provide power during a blackout, or to take a customer off grid, or even to day trade electricity where we have a higher rate during the day and a lower rate at night, where we buy low and sell high, we would be completely missing the primary application of batteries, which is a grid connected battery, particularly for the commercial market. However, at the same time, we see residential solar policies being scaled back, those outflow incentives being scaled back. And that creates many markets where it is as economic to go off grid as to remain grid connected. So the goal of today's program is to kind of understand where solar design kind of falls short as far as battery list design goes, get a better understanding of the battery specific solar array components, and also talk about the applications and economics of these systems. I work out of Mississippi. Mississippi is a very solar unfriendly market, and there's real reasons for that. Mississippi is a rural electric grid, and it has more miles of power line per customer than a typical region, and certainly than a typical state. And so if there's simply not enough money and not enough customers to spread out the revenue loss associated with solar to the grid operator, there's not enough budget to just spread that out across all customers. And whether or not that's a good thing or a bad thing, I mean, many would argue that solar is one of the cheapest ways to provide new capacity to the grid. At the same time, grid operators could argue that in a rural grid like Mississippi that has not seen a lot of population growth, that they don't need new capacity and that they need to keep paying off their existing capacity. So even if solar is cheaper than any other new technology, adding that solar capacity to the grid still raises the cost of electricity in an area that operates well below the nation's average income. And so, even what I'm trying to say is there are noble reasons to pass anti-solar policy, and for the individual solar consumer, they might find themselves in situations where they just throw their hands up in the air and say, "Hey, I'm getting a raw deal. I'm disconnecting from the grid." Or you might be subject to a rate structure that is particular to your region and find an opportunity of where solar and batteries fit in to provide a very economic application for solar where one is previously not really well known to exist. In other words, the design parameters for a battery system are completely different for a battery-less system, and some utilities make the mistake of making their rate structures so against a battery-less solar array that they almost go too far in the opposite direction, and it results in a rate structure that is incredibly friendly for a battery-based solar design. And so we're going to talk about all of those opportunities in class over the next day or two. Now, the battery market itself is exploding, which if I've been in the solar industry since 2008, and I'm used to this, triple digit annual growth rates that we saw in 2007, 2008, 2009 in the solar industry. We're seeing the same kind of triple digit growth rates in the battery industry. I read the battery storage reports and I chuckle to myself over some of the numbers because, I'm doing 100 kilowatt hour battery banks in Mississippi, and I know that none of those numbers are showing up in these reports. And these reports are always erring on the conservative side, even though they show incredible growth. So it's definitely the growth market. And this is at a time when the growth in the solar industry is leveling off for a variety of reasons. And so if you want to be in a market that is experiencing jaw-dropping exponential growth, the battery market is the one to pay attention to. And some of this growth leveling in the solar industry is a result of policy, of course. I get into my solar class on how solar is as much a computer technology as it is a green energy technology, going back to the material supply chain. And for various reasons that have to do not with green energy policy, but the computer industry, we can see the long-term growth projection for solar is being positive. But we are in an energy industry where, like it or not, policies will pick winners and losers. And we would be ignorant to assume that those policies did not impact our industry. For example, way back in 2008, the tax credit for solar was reinstated by the George W. Bush administration. And that tax credit was supposed to expire at the end of 2016. Now, in reality, in 2015, the tax credit was extended on out into the future. But way back in 2008, it was kind of foretold that 2016 would be a banner year for solar because project developers would kind of wait on their projects and plan them for 2016 when module prices would be cheaper, or take projects that normally would be occurring in 2017 or 2018 and schedule them for 2016 because that's when the tax credit expires. And even though the tax credit was extended in 2015, that didn't give especially the utility scale sector enough time to kind of switch around and rearrange their project schedule. So what we saw was a huge spike in solar in 2016, and even though maybe the residential market kept growing and the commercial market, actually the commercial market's a little bit different. If we can look at what's in this dark blue, this kind of mid blue, this is the commercial market, and it's been kind of just stagnant, whereas we see a little bit of growth in residential and a lot of the new growth in the sector has to do with utility. And what we see is that the utility scale sector was much more impacted by these subsidies and policies than other sectors. In fact, you go back into the time in the era in the solar industry when the tax credit did not exist. And what we see is that the residential and commercial market were a much larger segment of the market than the utility scale sector back at that time. Now, what was interesting about 2007, the year right before the tax credit came into existence, is the commercial market segment was actually, for the very first time, the largest market segment in the industry. In 2007, for the very first time, the commercial market had eclipsed the residential market in terms of solar application. And the utility scale market, for that matter, was back in 2007 less than 10% of the market. And now today it's the bulk majority of the market. And so what that tells me is if we're going to talk about solar subsidies, what I would say is the utility scale market is the most exposed to subsidization. Now, the counter argument is that utility scale can take advantage of economies of scale. And so it's much cheaper to do a utility scale project than it is to do a residential project. But at the same time, it's a lot cheaper to do a commercial market than it is to do a residential project. And we didn't see the same amount of growth in commercial as we did in utility scale. And the answer all has to do with policy. Our policies were better for the utility scale market in the sense that a utility and a solar developer and a hedge fund could get together, and the hedge fund could say, we're paying billions of dollars a year in taxes, and now there's this uncapped, unlimited solar tax credit. Why don't you give us a power purchase agreement where you buy all of our electricity for a certain rate, and we'll scale up the solar industry. And the same amount of policy access for, say, the commercial market did not exist. And so I think what is particularly interesting about that is the solar tax credit combined with batteryless solar business models really benefited the utility scale sector, and the residential, but in particular the commercial market segment, went from being the largest application of solar to the very smallest application of solar. So if there's one market that existed before the tax credit that got punished by the tax credit, it's the commercial solar market. Now, here we're looking at some project budgets of, again, batteryless solar, and so we're about to get into batteries. But one thing I want to point out is the cost difference between, say, the utility scale solar market and the residential solar market. The cost of the solar module itself is about the same. It doesn't really cost more to buy a residential solar module versus a utility scale solar module when we're talking about factory gate pricing. Now, there is a little bit of a soft cost, which is the supply chain markup, where you might get a markup from your distributor, whereas a utility scale project may be purchasing directly from the manufacturer. But that said, the supply chain for solar is traditionally it's oversupplied, which means we have a lot of modules, which means the manufacturers are just trying to almost sell their modules at cost just to stay in business. and it produces a very competitive supply chain, which means the average markup for a solar module is actually not that much. Um, yeah, inverters do cost more. I guess the inverters in the dark blue, the residential inverters do cost about twice as much as the utility scale. But what we see is, say commercial inverters cost about the same as utility scale inverters, and so the economies of scale of solar um, don't really apply to the specialty material. And certainly by the time you get into the commercial segment, the price difference between the modules and inverters are about the same as what you would pay for utility scale modules and inverters. And similarly for racking, yes, residential racking does cost a little bit more than utility scale racking, but not by a substantial portion. The vast majority of price difference between, say, rooftop solar projects and utility scale projects is this development cost, how much profit the developer is making, the overhead costs, the insurance rates, the permitting costs, the mobilization costs, and then of course the supply chain as well. And for that matter, the design and engineering cost is just a small sliver of project costs at the utility scale level. Whereas, as engineers, if we're providing a stamp on a residential project, there's a minimum billing rate that we're going to charge for it to be worth our time and liability. And so the material itself is the key issue. It's not unheard of for you to be able to roll up your sleeves and do a little bit of competitive bidding in the supply chain and be able to obtain pricing for your materials that is somewhat similar to what the utility scale market can deliver. And so that gets us into this kind of question of, well, why is the utility scale market growing so much and the residential and commercial market not? And it really has to do with policy, where you can get a very streamlined agreement between a utility and a major project developer for a major power plant, and that industry is kind of developed. Solar has turned consumers of electricity into power producers, and it's resulted in the need for new policies to be established to determine what the relationship between someone who was traditionally a buyer of electricity, now they're a seller of electricity, and what are they going to be compensated for that. A solar array and your building consumption occur at different times. So in the middle of the day, even a small solar array can produce outflow onto the grid. And what this outflow is compensated at is called your net metering policy. And there's really four flavors of net metering. There's the unlimited rollover minutes where all of this export is just kind of credited against the next instant in time, where you take your outflow and your inflow and you just subtract them from each other, and basically you're trading kilowatt hour for kilowatt hour. So that's kind of the unlimited rollover minutes is your unlimited net metering plan. Similarly, an annual net metering plan would say your rollover minutes are eliminated or just wiped off the table at the end of the year. Or you might have a monthly plan where on a day-to-day basis, it might be 3 p.m. and your solar array's on and your air conditioner is on and you're not outflowing onto the grid, and then 15 minutes later, your air conditioner turns off, your solar array remains on, and so now you're outflowing onto the grid, and then 15 minutes later, your air conditioning turns back on, and so you're trading that inflow versus outflow on a minute by minute, hour by hour basis, and then at the end of the month, any surplus credits are wiped off the table. And when I say wiped off the table, generally what that means is that the power company buys them at what's called avoided cost. Now, avoided cost is the raw material price of coal, the raw material price of natural gas. So your Public Utility Commission will average these numbers together and come up with what is the cost of buying the raw material for the average unit of power on the grid. And they'll say that is the avoided cost. And there's a federal law that mandates that clean energy be purchased at avoided cost. And so if your energy is cleaner than the average grid content, you're allowed to interconnect to the grid and push it onto the grid and clean the grid. And the compensation rate is the raw material cost of the less clean energy resource. So that was kind of a compromise that was struck. And actually, the power company is allowed to subtract an administrative fee from that avoided cost. So technically, the very least that a utility is federally obligated to purchase solar outflow at is below the raw material cost of coal and natural gas. And that was traditionally a non-controversial policy. It was kind of like a common sense compromise for allowing mandatory buybacks to come into existence. At the same time, in some markets, the utility scale solar projects can now be developed at avoided cost, and that is causing some fear that traditional fossil fuel utilities may go out of business. Anyway, what is in vogue now is to roll back net metering. And I've been talking about this in the solar classes for some time. It's rare for your customer to have an unlimited net metering schedule. What is more likely is if your state Public Utility Commission, so this is a state by state policy. So there's a different net metering policy for Kansas City, Missouri and Kansas City, Kansas. I mean, it varies by state or by, electric grid region. But even so, even if you have net metering, it's rare to have unlimited net metering. What is more common is to have annual net metering, except the utilities can often define what the definition of the end of the year is. And many utilities will define the end of the year being the end of March, because it is in spring and in fall that you generate surplus, and it's in summer when your electric loads are high, or winter when your solar production is low, when you don't produce the surplus. And so if I define the end of the year being the end of spring, then I'm going to generate surplus in winter. Well, I'm not going to generate surplus in winter. I'm going to generate surplus in fall, and it's going to roll over into winter. And I may or may not use all those credits in winter, and they'll roll over into spring. And then I'm going to generate more credits in spring. And generally, under an unlimited net metering policy, you would use all of your surplus credits from fall and spring in the summertime. But if I'm canceled out right at the end of spring, then really I don't have anything more than what's a month-to-month net metering policy. And so under a month-to-month net metering policy, the most cost-effective array may be one that eliminates your springtime electric bill, but doesn't do 100% of your electric bill. And so actually I'm not completely opposed to policies like month to month net metering. I mean, the solar industry would obviously prefer a limited net metering, but a month to month net metering plan, basically says that, hey, if you want to eliminate your entire electric bill, you're going to have to sell the utility some electricity at avoided cost. And so it does force kind of a compromise to those who want to do an array large enough to knock out their entire electric bill, to also allow the utility some profit motive to do so. But what's most common today is for utilities to cancel their net metering policies, and that means the instant, at 3 p.m., when your air conditioner turns off, the instant your solar array is outflowing onto the grid, you are only being compensated avoided cost, and in some cases, avoided cost less an administrative fee, so less than avoided cost for that outflow. And at that point, solar becomes very uneconomic, and it forces you into this issue where you need to do small arrays, but then again, small arrays don't get the economies of scale of large arrays. And so if you don't have a net metering policy, the utility can effectively prevent consumer-owned solar from coming to market under a batteryless solar array. Now, that doesn't mean solar's not getting cheaper and cheaper and cheaper, and that doesn't mean that in regions where there is net metering, solar's exploding, but it's almost like they're pulling back a rubber band and just delaying the adoption of solar in a given area by not providing the customer with a rate structure that is appropriate for driving the growth of solar in an area. And that particularly that applies to rural areas, which is kind of ironic because it's in rural areas that you need distributed power, where pushing power all the way down the line of your distribution circuit becomes quite costly. And so it's kind of an irony that in rural areas like the Tennessee Valley Authority region, you get monopoly co-ops with very bad anti-solar policies, even though they really should be the ones that are implementing the technology first. And so you might find yourself wanting to develop a solar project, but being stymied by your local policy. Now, in some cases, policy can increase the value of solar. So let's talk about a time of use rate structure. In a time variable rate structure, you will have a higher rate during the day and a lower rate at night. And so if your average electric rate is 13 cents a kilowatt hour, it may be 23 cents during peak and 6 cents off peak. So this is kind of a Southern Company, Georgia power rate structure. Sometimes you have to watch out for these time of day rate structures because they'll increase your on peak time and not really decrease your off peak time. And so you have to be careful if you're voluntarily opting on to a time of day rate structure that you're not just shooting yourself in the foot and increasing your electric bill for no reason. That said, in many cases, particularly those where either you're not at home during peak times, like if you work a evening shift at work, or if you live at home full time and you can actively manage your electricity use, such as retirees who can say, okay, well, I'm going to run my thermostat a little bit high during peak times and then only crank the AC during off-peak times. I'm going to wait to run my dishwasher or do my laundry until off-peak times. Those customers can benefit through time of use metering even without generating their own power. And in general, a time of rate structure will increase the economics of solar because you can generate during peak times and avoid that higher rate. And then, then your solar array is saving you during the day, and it's also saving you at night. And net metering combined with time of use metering is not a perfect policy, because it says, okay, well, if I'm generating at peak times, do I get a peak credit, or do I get a retail credit, or do I get an off-peak credit or an avoided cost credit? I really think that net metering is kind of an obsolete policy. It's been around since, actually it's been around since analog meters. Analog meters would just spin forward or spin backwards. Here in Mississippi, we don't have any kind of net metering at all. And when I have a customer go solar, that is the time when the utility comes out and swaps out the analog meter with a digital meter that gives them avoided cost buyback instead of what would be inherent net metering. Even if you're an advocate of net metering, it would be foolish to think that net metering is going to be around as a long-term policy. For that matter, net metering encourages you to produce energy not during the times when it's needed, but optimized for annual production. And so you will point your solar arrays due south at their ideal tilt angle in order to get a lot of power in the spring and in the fall when you don't really need it. Whereas a more shallow tilt angle might skew your production towards the summertime when your array would be producing less outflow. In fact, in our solar class, we talk about how if you only have a month-to-month net metering policy, or if you don't have a net metering policy at all, going with a shallower tilt angle can be just as cost effective as going with a ideal tilt angle, because it's not just about how much energy you produce, it's also about how much your cost of electricity is. You multiply the two together to get your cost savings. And in fact, the price of electricity varies much more greatly throughout the country as your solar production. And so it's the price of electricity that drives the solar market more than, whether or not you're in a sunny region or a cloudy region. Germany would be a great case in point. They've been a historic leader in the solar industry, and it's like Portland or Seattle get about the same amount of sunshine as Germany. It's just that in Germany, their cost of electricity is 3 times the national average as it is in the US. So even though they get below average sunlight, they still have an economic motive to generate solar power. So given what we know about rate structures, and say, let's go back and look at this time of use metering differential where we might have a 23-cent rate and a 6-cent rate, you might think, well, what happens if I charge a battery during off-peak times and then discharge it during peak times? Might that be cost effective? And in fact, you wouldn't even need necessarily a solar array to do this. So can you just take a bunch of batteries and wire them up to your home and run your home during, off-peak times, charge up the batteries, discharge them during peak times? And the missing factor is, how much does it cost you to run those batteries? And looking at some battery pricing, let's assume that your flooded lead acid batteries, you go and do some pricing, and maybe golf cart batteries cost less than this, maybe $110 a kilowatt hour, but they don't last very long. And then you get into what are called renewable flooded lead acid batteries or premium flooded lead acid batteries. And we're going to learn a lot more about those during this program. And they'll run you around $160 per kilowatt hour of storage capacity. Then you get into forklift batteries. These are called industrial flooded lead acid batteries, and they cost more than your premium line flooded lead acid, but they also last longer. They're rated for more cycles. And so we're going to get into the difference between the two. But the short of it is the industrial flooded lead acid costs less per total lifetime use than the premium batteries. And so you're kind of trading upfront capital cost against a longer lasting, ultimately more cost effective battery. Similarly, you get into lithium ion batteries or even top shelf lithium ion batteries, and your levelized costs continue to drop, except your upfront cost continue to rise. And so there's this kind of a difficulty of, if you want a battery that is less expensive to operate over its lifetime, you have to pay up the wazoo up front. And that kind of forces you into a cheaper battery in terms of upfront capital cost that costs more to cycle. And so if you have this concept, let's just assume for a moment that you're going with the Tesla Powerwall. It's a popular option. It costs about $410 a kilowatt hour of storage capacity. Let's say you buy about 2 days worth of storage. That'll run you through an extended blackout. You could probably get away with less than that if it's a grid connected battery. I mean, most power outages are not for 2 days. They're for less than that. And I say 2 days with solar. I guess this might be 1 day without solar. Well, you look at that $407 a kilowatt hour pricing, and you divide it by its rated kilowatt hour cycles, and you get your levelized cost of energy of being about 15 cents a kilowatt hour. And so you then go and look at the price difference between peak and off-peak energy, and you're not saving the difference between 23 cents and 6 cents. You have to add in your levelized cost of cycling that battery into the soup. And so you go and you add 15 cents on top of that, and quite obviously you get closer. You're almost just spinning your wheels by charging the battery off peak and then discharging it on peak. You're really not saving any money. You're just using your battery and trying to get your useful payback, recover your cost of your investment. But there is a limited warranty on these batteries, or a limited life on the batteries. And if you take the warranted performance of that Tesla Powerwall and you divide it by its cost, what you realize is in most cases, you're going to need a time of day differential that is not 6 cents versus 23 cents, but that is more like a 30-cent differential in order for that day trading of electricity to make economic sense. And so basically, what you need in order to get any kind of reasonable payback, and this is true with solar, and it's also true with batteries, is that the levelized cost of the on-site application needs to be about half the effective rate, the effective retail price of electricity. So, if your solar has a 25-year life, it's going to need to have about a 12-year payback in order for someone to open up their wallet and actually buy it. In fact, the economics get even more harsh when you get into the commercial market for energy efficiency upgrades. They want more like a 4-year payback. And for that matter, when you go and you look at the time of use rates, they're not available every single day of the week. They're generally available Monday through Friday. So only 5/7 of the week, only 70% of the week. And then they're not available every month. Sometimes they're only available during the 4 peak summertime months. And so instead of being available for 100% of the year, they're available for maybe 40% of the year. And then they're only available for 80% of the week, excluding holidays, or 70% of the week. And so they might effectively only be available, this opportunity to day trade electricity may only be available for 30% of the year, even when you have access to time of use metering, and not all customers do. And so what that basically does is it says, well, what we need to do is we need to look at markets where the cost of electricity is high in order to see where, batteries will first be cost effective. And of course, there are stereotypical markets where the cost of electricity is high, such as Con Edison, New York, or out in California, the East Coast, the West Coast, ultra remote areas like Alaska or Hawaii. Then again, you can find some markets like, I guess New Hampshire, where you start to get up to 20 cents a kilowatt hour. Let's see. I thought I had another market here where, what we find is that it's really in rural areas outside of California and New York where the price of electricity goes up. And so what we want to do is take a closer look at rural markets and rural electric rate structures in order to find where battery applications are going to be cost effective. Now, another way to make batteries cost effective is to have subsidies. And there are some subsidies available in California and in New York for battery systems. So in New York, if you add a battery to your solar array, it'll give you an additional $50,000 of battery of budget for your incentive. And so basically in New York, you can add a $50,000 battery to your subsidized solar project and not really see a huge, you'll get all that money back effectively. In California, they provide what is basically a 30% state tax credit on batteries. And so that's actually it kind of distorts the market, because just like in the rest of the country where there's markets that have historic solar incentives, and then there's markets which don't have any solar incentives. And so if you're in North Carolina, in the past they've had a state tax credit that was 35% for solar, and that would combine with the federal tax credit of 30%. Or Louisiana, they had a 50% tax credit for residential solar that would combine with a state tax credit of 30%. These customers were getting tremendous paybacks of their solar arrays, not necessarily because of the cost savings on their electric bill, but because the subsidies were covering the bulk majority of the system cost. And what that means is that you can go and buy the Mercedes Benz or the Ferrari of solar because 80% of it is being paid for by someone else. And so you have to be a little wary of the battery solutions that are being used in California, because when you combine the federal tax credit for solar, which also applies to the battery bank if it's charged by solar, and then you combine the California state tax credit for batteries, which is an additional 30%, and then you throw in the fact that California has the most expensive electricity in the country, you can have customers go for the top shelf battery solution rather than something that is more of a economically based decision. And so you'll see lots of lithium ion batteries and even top shelf lithium ion batteries being installed in California. And for the time being, that's where the battery market is, because again, batteries are very expensive. And so you'll go and ask the battery design software companies, hey, which batteries are being modeled most frequently? And they'll tell you, well, it's lithium ion batteries and it's all out in California. But that doesn't necessarily mean that's the same battery solution you want for the middle part of the United States. All right, let's put that on the shelf for a minute and talk about some system designs, system configurations. One kind of popular debate in battery systems is, are you going to do what's called an AC coupled system versus a DC coupled system? Now, an AC coupled system is where you have a solar inverter and you have a battery inverter, and they're plugged in to the same electric service panel. And so you might have your electric service panel with a breaker slot, and you put in your solar array here, and you put in your battery array there. And so that might mean that you have an existing home with a solar array on it, and you want to go and add batteries to it. And so you just go and add a battery on its own inverter in parallel to the existing solar array. And that's called AC coupling. And it's allowed. You're allowed to do this. Now, in this case, this is a SMA battery inverter and an SMA solar inverter, and you'll run Ethernet cable between the two so that they can talk to each other. And one advantage of that is when your batteries are full and your solar array is on, the danger is that you can backfeed the battery. And so what the battery inverter will do is it'll send a signal to your solar inverter, and it can do one of two things. And if you don't have this Ethernet cable, your battery inverter will actually send the signal through the power line into the inverter. And what it'll do is it'll take the 60 hertz signal that your grid is operating at, and for a very brief period, it'll change the frequency, maybe to 59 hertz. Not enough for your electronics to really notice any difference, but enough for the inverter anti-islanding detection. So there's control circuits in your solar inverters to the instant that there's a blip in the electric grid, it turns off. And so your battery inverter will use that same protection that's part of a UL listing in order to trick the solar inverter into turning off. And so when you have a battery inverter that is different than your solar inverter, they can still use this kind of trick in order to turn the array off so that you're not overcharging your batteries. Now that's for a grid connected battery inverter and a grid connected solar inverter. If you go and use an off-grid battery inverter, it may not have the same controls inside it. Now, what's interesting, if you use an elegant solution, like if you use the SMA battery inverter and the SMA solar inverter, it'll actually just dial back the solar array and maybe only turn one circuit off. Say, hey, our load is at 4 kilowatts and our solar array is at 8 kilowatts. And so in one circumstance, you would be turning off the inverter and then drawing down the batteries and then turning the inverter back on and then filling up the batteries. And that's using your batteries. That's cycling your batteries. That's taking life out of the batteries. In another circumstance, the batteries are full and your solar array is on and your home is using 4 kilowatts of load and your solar array is at 8 kilowatts and your battery inverter tells your solar inverter, hey, just dial it back a little and dial it back to 4 kilowatts. And so that way you're using your solar array and you're not using your batteries during the day when your batteries are full. And so what we can see is that there is an elegant solution and there is an inelegant solution to retrofitting existing solar arrays onto, or batteries onto homes where there are existing solar arrays. If you have a Fronius inverter and you don't have a Fronius battery inverter, there is a battery solution for you. Although it is better if your solar inverter manufacturer also has a battery solution so that you might be able to achieve a more elegant design. It's not a deal breaker though. So that's AC coupling, is when your inverters are located in parallel next to each other. Now there's another configuration called DC coupling. And DC coupling is where you have a solar array on a charge controller, and then that on the DC side is connected to your battery. And so your solar array is connected to the battery before it lands onto the inverter. So the solar array and the battery are connected to each other on the DC side rather than on the AC side. Hence it's DC versus AC coupling. And so traditionally there's a box called a charge controller that the solar array lands on, and then it goes into the battery, and then it goes from the battery into the inverter. Now this company is called Pika, and Pika is they put what looks like a DC optimizer underneath every single. Well, actually, what's interesting about Pika is they only put one DC optimizer on the entire circuit, whereas like SolarEdge does a DC optimizer on every single module. So the Pika solution is a little bit cheaper than the SolarEdge solution technically. Now, SolarEdge has huge economies of scale in production. Pika is more of a startup company. Why I mention that is the DC optimizers in the very popular SolarEdge solution, they are charge controllers. They regulate the voltage going back to the inverter. And so the SolarEdge solution, they have a DC coupling solution that just taps on to that DC home run with their battery. And so SolarEdge does have a good path towards DC coupled batteries through a charge controller that is already on your rooftop. In other words, maybe going to adding batteries with a DC optimizer system. In our solar class, we've said, okay, well, DC optimizers are more expensive than not having them. And there are certain performance advantages like shade optimization that they bring. Well, then when you go and you add a battery, you're going to have to go ahead and buy a charge controller. Now, it's cheaper just to buy one charge controller for a whole bunch of modules than putting one on every single module, except that SolarEdge is very far ahead of the market on this, and so they've been able to ramp up their production. So I mentioned Pika because it's kind of interesting. They're the only ones I know that have a roof-mounted string optimizer. Other charge controller solutions really have what almost looks like another inverter. It's just that the solar array lands on the charge controller before landing on the battery, and then the battery and the charge controller share a common bus that the inverter is also tapped onto, and then you go into your load. And so that begs the question, well, which is more cost effective? Is a DC coupled solution versus an AC coupled solution? Which is more cost effective? Well, in an AC coupled solution, you have to buy two inverters. And the charge controller, regardless of its type, it does not have all of the parts that an inverter has. An inverter does a DC to AC inversion, whereas a charge controller, all it does is take the DC and converts it to another DC voltage. So the charge controllers are cheaper than inverters. And so if you're starting from scratch and you're buying the whole solution, DC coupling should save you a little bit of money. The thing is, it's not very much money. You know, the price difference between a charge controller and a full-blown inverter is not very much. In fact, you know, the pure string inverters that don't have any bells and whistles have been on the market for years and years and years and years, and solar charge controllers have remained kind of a freak, niche, off-grid, weirdo specialty product because the vast majority of solar arrays installed today have not had batteries and therefore have not had charge controllers. So even though charge controllers technically should be cheaper than their inverter counterparts, they really aren't. And so from a cost perspective, AC coupling versus DC coupling is so close together that it really does not justify a decision one way or the other. But there are technical reasons on why DC coupling makes sense, and there are technical reasons why AC coupling makes sense. If I'm doing off-grid, I want DC coupling. And the reason is, let's go back to our AC coupled solution. Now let's say I have a solar array on one side and a battery bank on the other. And let's say for the time being that I'm off grid. And let's say for the time being I don't have a generator. So I just have a off-grid home with a solar array and a battery bank. Here's my solar array. Here's my battery bank. Your solar array needs to see a signal to turn on. You know, almost like a generator, you either need to crank the generator or have a battery to start the generator. Your car, you can't just go and turn the key and have the motor come on. You know, it needs a starter to turn on. Your solar array needs a starter to turn on. The grid is the starter that gives your cheap solar inverters the signal to say, hey, the grid's on, I'm going to turn on. Now, in an off-grid setting, your battery inverter can provide that signal instead of the grid. You know, you could actually land an off-grid battery inverter onto a generator panel where here's your main panel and you have your main that the grid lands onto. A generator panel has a little breaker here that has a plate that puts you on a switch that says either the generator is going to be on or the grid's going to be on. You could go and get a cheap battery inverter and put it on that interlock panel, and during a blackout, go flick your main off and turn your battery inverter on and turn your solar array on. I mean, there are cheap ways to kind of jury rig your off grid or your battery retrofit. But the problem is with an AC coupled off grid system is if my solar array is off because it's nighttime and my batteries fully drain down, well, now my problem is my battery inverter can't turn on because my batteries are drained, and my solar array can't charge my batteries because my solar array is off. And so what you want is that kind of direct drive of DC coupling between the solar array and the batteries, so that when the sun comes back up, you know, your charge controller, which is not connected to the grid, it's not connected to that AC side, it's completely isolated from this grid. This distribution panel is a little bit misleading. There's a DC bus on this distribution panel that gets wired into the battery, then wired into the DC side of the inverter. And so because the charge controller is not connected to the grid, it can turn on as soon as the sun comes up and then charge those batteries back up so that the inverter can turn on. And so DC coupling is the better solution for off-grid. Is it the only solution for off-grid? No. I mean, the easy way around this, most off-grid arrays are going to have a generator. And so if your battery inverter runs out of batteries, you could always crank the generator and charge the batteries back up and provide the grid signal for the solar array to turn on. So you could crank the generator just for a half an hour if the sun's up, to give the batteries enough juice to maintain the grid while the solar array supplies the load and charges the batteries back up. So, you know, do you have to have DC coupling for off-grid? No. You know, you could have a generator instead. You could have two battery banks instead. You know, that sounds kind of weird, but often your generator itself is going to have a separate battery just for starting and stopping the generator. So in an off-grid setup, you might have two battery banks anyway because you have the generator. So DC coupling is kind of the more elegant solution for off-grid, but it's not the only solution. If you have an existing solar array with an existing inverter and you want to go off grid, you know, it's just as acceptable to do AC coupling. In fact, there are some reasons to consider AC coupling for off grid, and the best reason I can think of is that sometimes your solar array is on a ground mount that's very far away from your home, and your batteries might be quite close to the home. And on very far away ground mounts, I really like the SolarEdge solution because it steps up the voltage to 600 volts. And just like high voltage power lines, you want high voltage for transmitting electricity over long distances. And so I might do a AC coupled SolarEdge system in order to push that, and just so that I can get that stepped up voltage at the ground mount array that's off in the distance. So, I'm kind of expecting that to be over your head. The takeaway is there's no hard and fast rule of thumb on which is better, DC coupling or AC coupling. But just by a nose in a horse race, DC coupling is better for off grid. Well, what about for grid connection? If your battery is connected, and I apologize for this being blurry, but if your battery is connected to the grid, so here's your breaker panel, and here's the power lines and your transformer, and you're connected to the grid for your home. It's your house. If your battery is connected to the grid, and if day trading electricity, buying low and selling high, doesn't really make much economic sense, what is the role of the battery? Basically, the role of the battery is just to hang out, and if the grid goes down, to go and start up the solar array. And so often you have to go and put in a separate critical load panel because this panel is connected to the grid. And so you don't put in a critical load panel because you just want to protect critical loads. I mean, really, you want to power your whole house. It's inconvenient just to have your refrigerator running or your air conditioner running when you could be providing a whole house worth of power. You'd want to power your whole house. On these grid connected systems, you commonly find a requirement like the SolarEdge system that says, oh, you have to wire a critical load panel, and we don't support off grid, we only support critical loads. And the reason for that is they need this transfer switch so that you have a completely isolated array from the grid. But the thing is, your power doesn't fail all that often. At least in the US, most electric grids are very reliable. And so you buy that battery so that during that one power outage that lasts an hour or two, you don't have to worry about, the food in your freezer thawing. If you have a Hurricane Sandy type situation, that, well, at least during the day, I'm going to have power. And so I'm not going to have all my food spoil. I can stay at home and ride out the storm. It's just that during the day, I'm going to have a lot of power. And at night, I'm going to have to dial things back and still be kind of camping inside of my home. But I have solutions. And for many, this is like they want to make sure that their on-site medical equipment, their oxygen machines, their medicine refrigerators stay powered up during that emergency. And so your battery bank is really taking the place of a backup generator. You're not trying to run a battery bank off grid. And so you might spend the extra $8,000 for a Tesla Powerwall instead of spending $5,000 on a generator. And even though the generator might be able to power your whole house, you still have to go and put gas in it. And your solar array is the gas for your batteries. So, even though you're not fully prepared for off-grid living with your grid-connected residential battery bank, that's not really the point. You're not trying to run your whole house off-grid. You're trying to provide some emergency preparedness. Well, for that matter, you're not really buying low and selling high either. And so what that means is for most of the time, you're not in an emergency. For most of the time, your battery is just kind of hanging out, not doing anything. In fact, the more that you run your battery, the shorter its life gets. And so if you're going to spend all that money on a battery, you may not want to cycle it unnecessarily. There is the concept of buying the battery, and even though it's not really making you money, you're cycling it just to reduce your electric bill. And even though that might not be the wise financial decision, you're really just doing it to get one over on the power company by having a low electric bill, even though that might mean you have to replace your batteries more soon. And I suppose one advantage of just kind of spinning your wheels with your battery bank is that the cost of batteries is falling, so that, even though you're replacing your battery bank sooner, you're getting your value back. And then 5 years from now, batteries are going to be cheaper, so you just replace it. Then again, you unnecessarily cycle your battery, and you might not have the capacity there during the emergency when you really need it. All of that's kind of beside the point. The point that I want to make is that on an AC coupled system, primarily the battery is just kind of hanging out, not doing anything. And so at that point, you want to look at your system efficiency. Now, your grid connected inverters, the electricity is coming out of the solar array, it's being processed by the inverter, and then it's going directly into your load, or it's being sold back to the electric grid. And if you have a net metering policy in place, you're getting a good deal for that electricity. So you go through this one-step process. This is the number one, where your electricity is being processed once before it goes into your point of use or being sold back to the grid. If this energy is going from your inverter and then into your batteries and then back out of your batteries and into your load, that's a 1, 2, 3-step process. And so if your goal is to charge your batteries and then use your batteries to run your home, that is going to be a less efficient process than simply running your home directly from the solar array or selling back to the grid. And so actually, when you go into a DC coupled solution for off-grid, generally your solar array is only on for, let's just call it 6 hours a day. You might have some solar installers will only tell you that your solar array is on for like 4 hours a day. That's not true. That's a number from PV Watts, and we'll show you where that comes from a little bit later when we get into our design exercises. But, rest assured, your solar array is turning on when the sun comes up, and it's turning off when the sun goes down. And the very early morning and the very late evening, your solar array is not at full power. And so, let's just call the hours between 9:30 and 4:30 your solar window. And so maybe you're getting good production out of your array for 6 hours a day. But your home is using power for 24 hours a day. And so the point I want to make is, in an off-grid setup, most of the power that you're using is coming out of your batteries and not coming from your solar array. And so you want your electricity to be processed once by the charge controller and then twice by the inverter before it goes into your home. You don't want it to be processed in an AC coupled scenario. You don't want it to be processed once by your solar inverter, twice by your battery inverter, and then 3 times by your battery inverter before it goes into your load. And so, technically speaking, in an off grid setup, not only does DC coupling provide you with that extra, if your battery bank runs out during the night, it automatically charges up the next day security, but a DC coupled solution in an off grid setup where you're primarily running off of your battery, DC coupling is a little bit more efficient than AC coupling. That said, in an AC coupled scenario, you're really not using your battery. And if you're really not using your battery, it's going to be more efficient for the electricity to flow directly into your load, only being processed once by your inverter, or what would otherwise be your inverter, your charge controller in your inverter, before it goes into your load or into the grid. And so the takeaway from this is that AC coupling is more efficient when you are interconnected to the grid. And DC coupling is more efficient for off-grid. And so when you look at utility scale projects and utility scale batteries, those batteries are commonly AC coupled because primarily they're not using the batteries to supply the load. Primarily, they're using the grid or the solar array to supply the load and not the batteries themselves. The batteries are only being used for a few hours a day or a few hours a week or a few hours a month. And so when you're not using the batteries for the bulk majority of the day, AC coupling is the better way to go. When you're using the batteries, in an off-grid scenario, when you're using the batteries for 2/3 of the day or 3/4 of the day, that's where DC coupling is the more efficient process. So in short, DC coupling is the better solution for off-grid new construction. AC coupling is the better solution for like utility scale plants or commercial batteries or even really residential backup batteries. And then, don't sweat it if you're retrofitting and you already have a solar array there with an inverter. AC coupling is still going to get you to the home plate when you're trying to, say, take a residential home that already has an existing solar array completely off grid. AC coupling is a good path forward. You don't need to throw everything out and start all over again. Okay, so let's talk more. I guess this slide is a little out of place, but that's all right. There's another configuration that's not AC coupling and it's not DC. It's not grid connected and it's not DC coupled. It goes by a different name, which is called grid assist. And so under the traditional kind of off-grid setup, you'll have your solar array, and that may or may not be AC coupled to your battery inverter. So either this is going to be a charge controller and it lands on the DC side of a battery inverter, or it's going to be a standalone inverter with that communication circuit running between the two. And then you have your electric service panel. And then if this is a grid connected system that is also set up for off-grid mode, you'll have some sort of transfer switch, whether that be a whole house transfer switch at where the power comes into the property, kind of like if you had a backup generator on a whole house transfer switch, or if that transfer switch is just on a critical load panel. But you might run into a situation where a utility says, well, if you are interconnecting a solar array to our grid for buyback purposes, we're going to charge you an interconnection fee and build, basically increase your electric rate. And in some regions, these monthly solar dedicated fees can get up to the value of basically what's like a 4 kilowatt solar array. And so there might be an instance where you are using a battery and you're sizing the solar array so that for the most part your home can run off solar in the battery, but you want to remain connected to the grid, but you want to avoid the grid connected fee. And so you might ask yourself, well, is it possible for me to disconnect my home during the day and reconnect at night and not have my solar array be outflowing onto the grid and actually not have my solar array be connected to the grid at all? And the answer is yes. And under that circumstance, we would kind of get rid of the generator here and say, for the most part, the grid is our generator. If our batteries get low, we'll charge them back up with the grid if we don't have a solar array here. And you take the solar array and you go and you land it on the other side of the transfer switch. And so the transfer switch will switch fast enough not to interrupt the power in your electric service panel. So there is kind of a interconnection called grid assist that is used in kind of punitive rate structures that are anti-solar. But this is something that I thought would be more of an issue when I was writing the program, but I haven't really seen a US application for it. It's more popular in Australia. And so basically they take the solar array and then land it on a transfer switch so that either the grid is feeding the home or the solar array is feeding the home, but not at the same time. What's kind of interesting though is in order for this transfer switch to work, you're sharing a neutral so that you can pick up on if the grid is up or not and automatically switch between the two. If you were to interrupt the neutral, then you would have to go and manually reset the transfer switch. And the reason why I mentioned this is, at least in my neck of the woods, Mississippi Power has ruled that a solar array is interconnected if it feeds the same circuitry as the grid. And so even though actually by their definition it's even harsher than this, even if you used a completely interrupting transfer switch that completely disconnects the home and the solar array is completely disconnected from the grid, some power companies would still rule that as a grid connected solar array. So, at that point, you're really having to completely isolate the two systems from each other. There's better ways to go around that. And for that matter, you get into when you're really facing a utility that has punitive solar policies. At some point, you just throw your hands up in the air and say, forget it. I'm just taking the customer completely off grid and not paying for that grid connection. And so we'll talk about some of that stuff a little bit later when we get into our off-grid discussion. We're still kind of introducing concepts at this point in the program. So let's talk about the commercial solar market. Commercial batteries are a brand new way of even thinking about solar. And I'm really excited about this market. I think this is the best market in the solar industry right now. On a commercial solar array, it's rare on a larger building for a solar array to produce outflow. So net metering is not really an issue for commercial buildings. They don't. Their demand is so high during the day. If your commercial facility has, let's say, 200 kilowatts of demand, and your solar array is, let's say 100 kilowatts, all we're doing is reducing the power level of the building during the day. We're not making it go all the way negative. And so solar is going to come through and reduce a building's demand. And peak demand often occurs right in the middle of the day at the hottest time of day. And so we have solar producing demand electricity at demand times. And we also have our facilities at the commercial level being billed under demand charges, where the maximum height of this curve reflects their most expensive electricity. And so you would think that that is a natural fit for solar. Demand electricity at demand times under demand rate structures. It should be a grand slam home run, knocking the ball, all the way out of the ballpark. And yet, the commercial market has lagged far behind the other markets. And the reason for that is that you could have, this is a sunny day. And this is a sunny day. And this is a partly cloudy day. And so what we can see is, if we were on a completely overcast day where our solar array isn't doing anything, our building demand would also be down because it's overcast and it's not as hot as a sunny day. And so our air conditioning is not as much as on a sunny day. But it's on these partly cloudy days where we still get the same facility demand as we do on the full sun days, except now one cloud comes and sits on top of our solar array right during peak times. And if our solar array turns off, our demand charge would be exactly what it was before, because our solar array is off for a 15-minute window. And these commercial demand rate structures are not the maximum demand every single day. The commercial rate structures are the maximum demand for just a 15-minute sliver. What is the maximum 15 minutes for the entire month? And so it's not that solar doesn't produce demand electricities at demand times. And it's not that we can't rely on solar to reduce the facility demand on a sunny day. It's that on a partly cloudy day, that might be one 15-minute window out of the entire month. That one cloud in the sky comes and sits on top of our solar array, turns it off, and our facility demand spikes through the roof, and we see no demand savings, even though 95% of the time our demand array is reducing our demand charge. There are zero demand savings because we have to control our demand 100% of the time. And so for the last decade, the commercial market has lagged far behind the residential and the utility scale market because we cannot control the demand of our facility with solar with 100% reliability. And that's where batteries come in and completely change the entire equation. And uh, utility regulators should be warned that this could cause an economic crisis in the industry because certain demand charges are so skewed towards high demand rates that the commercial battery market is primed for being disrupted and upset. So what we're going to do now is take a 15-minute break. It's 12:30. We're going to pick back up at a quarter till. Really, we're going to pick back up at 13 till. So we have 2 minutes after a quarter till. Let's take a 15 minute. So anyway, I didn't really miss anything other than what I wanted. Really, what I wanted to illustrate was we got area under the curb. That's your residential billing structure. That's the kilowatt hour. And then the very top of the curve is just the y-axis, is just kilowatt. And that your commercial rate structures are kilowatts plus kilowatt hours. And so whereas 100% of the residential bill is calculated by kilowatt hour, maybe it's half kilowatt hour, half demand charges for commercial, but not necessarily. And so demand charges vary throughout the country. And what's kind of ironic is that out here in Mississippi, I'm paying 12 cents a kilowatt hour. But for the commercial customers, the power companies have chosen to primarily make all of their bill demand and almost none of the bill energy. And so here in Mississippi, we're paying 12 cents a kilowatt hour for our electricity, but we get into $20 demand charges and like maybe 3-cent energy charges. And in New York City, you get into $20 demand charges, but they also have 12-cent energy charges. And so what I say to my customers in Mississippi is that we have cheaper electricity in general in Mississippi than in New York, but commercial customers in Mississippi are paying New York City demand charge pricing. And so just because you are in a cheap energy market does not mean that your commercial customers do not have sky high demand charges. This is just a survey of demand charges throughout the country. And, it's common, like in, say, Ohio, to see demand charges in the $6 to $8 range. And then, just across the border in Tennessee, you can start getting into $18 demand charges. It just really depends on how the utility wants to chop up the rate structure. And I would say in general, you get into higher demand charges when you get into sparsely populated areas where they want to have a big manufacturing center. They say, well, your facility is going to put a lot of demand on the grid, and we're going to have to wheel in that electricity from 200 miles away to supply your facility. And there's going to be a lot of voltage drop and line loss associated with that. And so we're going to charge you a high demand charge accordingly. And so let's just do an example bill here. Let's say we have a 6-cent energy charge and a $10 demand charge plus a fixed fee of $150. So this would be like a Ohio rate structure. We say 1 hour of electricity is at 6 cents a kilowatt hour, plus cycling our battery. Let's say we're using flooded lead or that Tesla Powerwall at 14 cents a kilowatt hour, and then it's not a perfectly efficient process. And so our electricity to charge and discharge a Tesla Powerwall might cost us in total 20 cents a kilowatt hour. But if my demand charge is $10 a kilowatt, and let's say I'm hitting my facility peak demand for 10 hours a month, and so I have to run that battery for 10 hours a month to reduce the peak demand of my facility. So 10 hours a month times 20 cents a kilowatt hour, it's going to cost me about $2 to run my battery, but I'm going to save $10 because I'm hitting that peak demand for 10 hours a month. And so I'm running my 1 kilowatt battery for 10 hours. 1 kilowatt times 20 cents is $2. And I'm reducing my demand by 1 kilowatt during that time. I'm saving $10 during that time. It's costing me $2. I'm saving $8. So I'm saving $8 to run my battery for, what's effectively 10 kilowatt hours. And so the generation rate of my battery at the time is 80 cents a kilowatt hour. And so what that means is that these demand rate structures, the higher the demand goes, it's possible not to completely eliminate your electric bill, but to implement what I call a solar peaker plant, where you aren't trying to do a solar array to eliminate 100% of the area under the curb. You're not trying to completely eliminate a facility's energy use. All you're trying to do is run a solar array enough to charge a battery, and you only are trying to give your facility a haircut and just chop off the spikiest spikes of your demand curve. And so, what's interesting is the more demand you want to take off a facility, the wider the triangle gets. And the wider the triangle gets, the longer you have to run your battery during that time. And that means the larger a battery you need. Whereas if you're just trying to run your battery during a very limited window, you can run your battery and then recharge it and then run your battery. And so you might just need a very small battery in order to substantially shave off that peak. And so whereas with batteryless solar, you need to do a very large array in order to achieve economies of scale, the larger your project gets under a solar peaker plant, you get into diminishing returns. Load leveling your entire base load with batteries doesn't make economic sense in the slightest, but doing a very small battery just to shave off the very tips of your load profile can make a lot of sense. It can be that your battery costs 20 cents to run, but it's saving you 80 cents. Whereas when you were doing that day trading of electricity under a residential rate structure, it may be costing you 20 cents to run in order to save 23 cents. And so batteries can be very, very cost effective under a commercial rate structure. So let's kind of look at some numbers here. We see that the average solar array per watt 1 watt of solar is going to produce between 1.3 and 1.4 kilowatt hours a year. And where that number comes from is a website called PV Watts. And we're going to come back to PV Watts. But if you just want to follow along, I'm going to put it into the chat. Well, here you go. So in the chat box, you can click the link to PV Watts and put in your area. So I'm going to put in Starkville, Mississippi. I think this is the most useful number to know in in the solar industry. I just recommend going into PV Watts and putting in a 1 kilowatt solar array, and just go ahead and just leave everything else the same. Don't mess with everything else. I mean, there's not going to be a huge difference if you want to play around with it and say, okay, I'm going to go with a roof mount instead of a ground mount open rack. The variability is minor. And in the solar class, we get more into these figures, but the standard value in PV Watts is going to be a very conservative number. And so just to get this kind of baseline estimate, just if you leave the numbers as is, it's going to give you a very conservative results. So I'm putting in a 1 kilowatt solar array. And in my area, we're producing 1,427 kilowatt hours a year. So in other words, for me, 1 watt of solar produces 1.4 kilowatt hours a year. And if we really wanted to get into it, if I went and I changed this to be from a south-facing solar array to, let's go with a southwest-facing solar array. So instead of 180 degrees, it's facing 225 degrees. What I can tell is the tilt angle and orientation of the array doesn't substantially change the performance of the array. You get all the numbers in here for more detailed analysis, and we're going to get into that detailed analysis when we talk about off-grid sizing. And this detailed analysis is also where your commercial design softwares go and generate these kind of detailed graphics. All of this data comes from PV Watts. So PV Watts, you get far enough into it, and it'll actually give you the interval data for the production of your array on an hourly basis. And if you can go into your electrical account, sometimes utilities provide this data at the residential level, but you always, if you are being billed by demand at the commercial level, you can get a year's worth of demand data from your utility, if not more. And so you take the PV Watts production values and then the building facility demand values and subtract the two to get a graphic that kind of looks like this. So back to our numbers. Throughout the country, 1 watt of solar is going to produce between 1.3 and 1.4 kilowatt hours per year. And so let's just say I'm getting an array at $2.50 per watt. Let's pull up our calculator. And so I'm a residential customer under an unlimited net metering plan, and I'm getting my array at $2.50 a watt. Now, what I like doing is I like taking my generation rate of the array, 1.4 watts or 1.4 kilowatt hours per watt per year, and multiplying it by kilowatt hours to get watts per year payback. And so in other words, 1.4 kilowatt hours per watt per year multiplied by 12 cents per kilowatt hour will give us 16.8 cents per watt per year. And then you factor in the 30% tax credit, 24 cents per watt per year. If I want a 10-year payback, I need an install price of $240 a watt. So what we're doing is this number in reverse. We're saying, okay, I'm at a $250 a watt installation price, and I'm dividing by a generation rate of 12 cents a kilowatt hour, and I'm dividing by 1.4 kilowatt hours per watt per year. So I guess these need to be reversed. So $2.50 a watt. And generally speaking, if you're in a rural area and you generally will have a low labor rate, and you should, through, if you know what you're doing and you do some competitive bidding, you do a large enough project, even at the residential level, you should be able to get this price. If you're in like a major city, you'll have a higher installation price. You'll also have a higher electric rate in general. But anyway, $250 a watt, take out the 30% federal tax credit, divide by 12 cents a kilowatt hour, divide by 1.4 kilowatt hours per watt per year, and we're at about a 10.5-year payback. And so what I'm trying to say in this slide is that at the residential level, at $250 a watt a year for a batteryless solar array under a net metered rate structure, you can get a solar array down to a 9 to 11 year payback. And some customers will go for that, not all. Some want more than that. Usually the customers who can afford to pay cash for their solar arrays are going to be fine with that payback, especially if they're finding you, not you finding them. They're wanting it, so they just want to be assured that they're getting their money back in a reasonable period of time. That's assuming net metering. That's assuming if you're getting a good amount for your outflow as well as your inflow. If you don't have net metering in place, you have to do a little bit more detailed design, and the payback can be pushed further out. So what we're trying to do right now is compare a reasonably priced solar array in most of the country under average electricity pricing, assuming net metering. What we want to do is compare that against the economics of a battery array at the commercial level. And so let's take that $250 a watt installation pricing at the residential level, and we'll say, okay, well, at the commercial level, that price might fall to $2 a watt, and then we'll put $1.50 a watt into our battery budget. And that's reasonable. You can get a battery bank commercial array for $3.50 a watt. In fact, you're likely to be getting this $3.50 watt commercial battery array. You're probably more likely to get that as a bid from a experienced solar contractor than right out of the gate. The experienced solar contractor might be bidding the solar array for a little bit more than that, unless it's a very straightforward kind of no muss, no fuss job site. Like a 2-story residential array might cost more than that. Commercial arrays, you're often dealing on flat rooftops. It's a lot easier to work on a flat roof than it is to work on a slanted roof. But what I want to show you is at the commercial rate, you're not paying 12 cents a kilowatt hour for your electricity. Let me move my calculator down a bit. So what I'm trying to say here is the residential electric rate may be 12 cents a kilowatt hour, and that might be 9 cents energy and $6 demand, or 6 cents energy and $10 demand, or 3 cents energy and $20 demand, in a market where you have a 12-cent average residential rate. Your commercial rate structures may look like this. Likewise, if you're in say the Northeast coast, where the residential electricity pricing tends to go up, your energy rates for your commercial customers will also go up, and your demand rates will go up as well. But the difference between the Northeast coast and, say, the middle of the United States is you're also producing a little bit less energy out of your solar array. That doesn't matter because the price of electricity is higher than the production loss. And so even though you're producing less, you're getting a quicker payback. And that remains true. The energy rates go up, the demand rates go up, and your payback goes down. So let's kind of do the math on our calculator here. If I'm at 350 a watt as my starting point, how many watts per year is my solar array going to save me? Well, at this point, you really have to go into commercial modeling software to get a hard and fast number on this. And really, the way that I do my sizing is I kind of first I do just kind of guess and check. I do a small array and a large battery, a large array and a small battery, a large array and a large battery, a small array and a small battery. And I look at which gets me the closest to a good payback, and then kind of fine tune from there on my optimization. But anyway, let's just go and look at just for example, this number right here at 350 a watt, and just make some basic assumptions. If I'm generating 1.4 kilowatt hours per watt per year, 1.4 times 3 cents a kilowatt hour, I'm only saving on the energy rate at 4 cents per watt per year. As if I was doing at the 12-cent rate, I would be 4 times higher than that. But I'm also saving at $20 per kilowatt. And this is going to vary based on your battery bank size, your inverter size, and your array size. But generally speaking, $20 per kilowatt times 12 months per year divided by 1,000 kilowatt or 1,000 watts per kilowatt is 24 cents per watt per year, plus the 4 cents from the energy rate. And so what I'm trying to say is if I multiply these two numbers right here, 1.4 by 12, I'm going to get something along the lines of 16 or 17 cents per watt per year. If I multiply this number by 12 months and then divide by 1,000 because it's kilowatts rather than watts, and then I do my 3 cents per watt per year multiplied by 1.4, and I add them together. In other words, I'm doing my X plus Y plus C rather than just Y plus C. So let me pull my calculator back up. So $20 a month per kilowatt times 12 months a year divided by 1,000 is 24 cents per watt per year, plus 3 cents times 1.4, let's just call it 4 cents per watt per year. That's 28 cents per watt per year. If I'm at 350 a watt, I back out the tax credit and then divide by 28 cents per watt per year. I guess I should have pulled out done the full extension here, but my payback is less than what it is at the residential level. And so the point of this slide is to indicate that you compare a batteryless net metered solar array to a battery commercial array, and it's actually the commercial solar array that has the better payback. It's the battery based commercial solar array that has the best payback in the industry. It has a better payback than a residential array, assuming net metering. And I don't think we can assume net metering anymore. Net metering almost across the board is being scaled back. The commercial array doesn't need net metering to happen. And what's particularly interesting about this is that this is a graph that was part of a study put out by National Renewable Energy Labs way back in 2008. So this is a long time ago. This was one of the graphs that I used to convince myself that if I got into the solar industry, people would buy solar arrays. Because at the time, the city of Austin was providing a solar rebate that was about 60% of the system cost. And the federal tax credit didn't exist at that time. So it was just the city of Austin rebate, but it was pushing what would be like a 28-year payback down to about 10 years. And we are saying, all right, well, solar is 0% of the market, and maybe 5% of the market would buy solar at a 10-year payback. And so, if we put out an ad for solar at a 10-year payback, and out of 100 people, 10 people are interested, and out of those 10 people, 5% will move forward. Well, maybe we have to go and flyer 200 people to get one sale, but we'll be able to drive solar up to a 5% market penetration rate at a 10-year payback. And once solar gets beyond that, the interest goes off. I mean, like geothermal is a great case in point. Geothermal is between a 15 and 20-year payback, and most people do not put geothermal systems into their buildings. But under the right commercial rate structure, where you get into the high demand charges, and it doesn't necessarily mean you need high energy rates. Really, all you need is high demand rates. That is where the paybacks start to get into maybe even 5 years or less. And so I had a student take this class in Colorado, and he said, well, I have a customer under a demand rate structure, and he's wanted to do solar for a decade, but because he's only being billed 3 cents a kilowatt hour for his electricity, he's never been able to do it. He went and modeled a solar battery and realized he could do a 4-year payback. So that customer went out and got a capital equipment loan and bought a solar array, and basically the cost savings from the array pay off the capital equipment loan. So we start getting into this higher level of market penetration if you're in a market where you have these high demand charges. So that's why I say the demand charges are the best in the industry. Now, one thing to consider, you notice my math was a little bit off on this level. What you really want are very spiky electric rates. And so this building is actually not the best demand customer. They can do a little bit of ultra cost effective demand savings. If we did, basically what is, in relative speaking, let's say their average max demand charge is reflected by this point right here. We would be basically leveling off maybe, let's just visually estimate it right here. 1, 2, 3, 4, 5, 6. We might be doing 1/6 of their facility demand. And if that is, let's just say 70% of their bill, we might be able to do a solar peaker plant that reduces their electric bill by 15%. And that might have just leveling off these little spikes, that might get you to a 4-year payback. But if we wanted to go any further than that, now our battery has to be substantially larger than what it would be just to shave off these spikes. And that's where we might get into the 10-year payback. So, the strategy would be to analyze the electric bill, go ahead and do the most cost-effective project that shaves off the very tips of the demand, and then gather data and watch the price of batteries fall to do a phase 2 down the road, and then maybe a phase 3, much further on into the future. Go after the low-hanging fruit with demonstration projects before and then wait for the price of batteries to fall, because the more you load level this curve, the more your battery bank needs to run, the more capital expense you're going to have to overcome for diminishing returns, because this is an exponentially growing curve, whereas your demand rate is a linear factor or variable. So where can we find demand rate structures that are high? Well, actually, it's been kind of funny. Utilities have been looking historically into demand rates as a way to thwart the solar industry. And so here's a list of states where you can find utilities offering demand rate structures at the residential level. So they're starting to peek into the residential market. In fact, years ago, there was a controversy where Arizona Power and Light was trying to force all of their solar customers onto demand charges. And the solar industry was saying, well, that's terrible, because what you're doing is watering down the net metering policy, and it's going to make solar less cost effective. But what we've seen from the numbers is that if they had gone with advocated for, well, okay, let's put solar onto demand rate structure, but let's make it a very high demand. We agree with you. Give us the highest demand rate structure you got. It would have given those solar customers a better payback, and they would have been able to put batteries into their projects sooner than under a net metered rate structure. And so what I'm trying to say from that is that demand rate structures can be very surprising to solar economics. In fact, there's a lot of solar installers out there who do not understand the economics of demand rate structures. But basically, once you get into $14, $15 on up demand rate structures, it takes, you can probably do a small solar battery. And in fact, in the instance of this customer in Colorado, his power curve did not look like this, where this would be like for a school building. So you have some base load and then pretty regular, you know, sine wave base loading. It goes up during the day, it goes down at night. What he was seeing is his demand was spiking through the roof in the early morning and then dropping back down to his base load and then spiking way up in the morning and then dropping back down to his base load. And these are the customers that are amazing for batteries because you don't need to run the battery that long. You still need some capacity, but that capacity is being used in a very cost effective manner because you're getting that demand charge down. And so in his case, this was his building heating load. And what was kind of ironic was, he could have just saved a lot of money by heating his building throughout the night so that he doesn't, he would use more energy by heating his building throughout the night, but instead he was using less energy to spike his demand, saying, okay, I'm only going to run my heaters for 2 hours right before the beginning of the day so that I'm not losing the building heat at night through radiative heat loss. Well, that's saving pennies, but spending dollars, because of the way, not from an energy efficiency perspective, but from the way he was billed for his energy. So slightly different meanings, but a huge impact on your electric bill. And so between a solar battery and then fine tuning, selling him some consulting services of, fine tuning when he should turn on his heating, it resulted in a very cost effective project opportunity. And we'll talk a little bit more about where you can go from there after we get through our modeling exercises. And so, for the past few years, the commercial market segment in this medium blue here has been kind of suppressed by these demand rate structures. And yet the commercial market has this nice hybrid of it costs less than residential because it's 10 times as big. A 100 kilowatt array can easily be installed for $2 a watt. I do $2 a watt installs in Mississippi because I have to. The policies are so bad that the arrays just do not make economic sense unless I get my price point down that low. One nice thing about doing projects in Mississippi is the rooftops are very simple. And so I rarely have a project that's on a 2-story roof. It's usually a 1-story big flat open rectangle or a ground mount with the customer having plenty of land. And so I don't have to get up on a roof and spend a lot of time on the roof. But you bet all I think about is how to make the projects go faster so that I can do the project in a day or two. And I force my customers to buy 15 kilowatt arrays because I just can't do a 5 kilowatt project at $2 a watt. I can't make any money that way. And so when you look at commercial solar, you're getting into 50 kilowatts, 100 kilowatts. You can get that dollar per watt cost down. And then they have the right rate structure to add batteries and get the payback. And I can tell you, most solar customers, they're in it for the economics, but they're very disappointed when they realize they're not going to be able to use their batteryless solar arrays during a blackout. And the reasons aren't well understood. I mean, you can say, okay, well, I'm connected to the grid, so I can't use the solar array during a blackout. But what if I go throw my main breaker? So now I'm disconnected from the grid. Can I then use my solar array? It's like, no, because you don't have all the parts that you need to turn the solar array on. You need a battery to start the array. You need a battery to maintain the array and balance out the production difference and to make sure that the power has a place to go. And so if you wanted a battery system, it's not that you're just buying the batteries, but some of your other system components become more expensive. And we're going to get into those costs too in this program. And so solar has been making their products cheaper and cheaper and cheaper and getting rid of the batteries and getting rid of the battery related cost components to get that cost down. And we've been relying on net metering as kind of a crutch to get the economics up. And now that the crutch is going away, it's getting harder and harder to do that batteryless residential solar. And even when you do it, the customer, has this expectation that they're going to be using the array during a blackout, and you're really just selling them an incomplete system. And to make it more complete, it's going to be more expensive. Whereas with a commercial array under a demand rate structure, it's now getting to the point where you can deliver them a system that will protect critical loads during a blackout and also aggressively reduce the demand charge on their electric bill in some cases where you have particularly spiky loads in a way that could be financed just through a regular capital equipment loan. So in agricultural facilities, you might have a grain mill that's only being run at 4 a.m. in the morning when you're feeding all your barnyard animals. And so if you have a manufacturing process that's only being used for a couple hours a day, but that's what spikes your demand and hits your peak demand charge, then that's a perfect application for solar. If you have a school building that's being used for 12 hours a day, that's going to be a little bit harder to do demand management. What you don't want are plateaus of energy use. You want spikes of energy use. And so kind of the basic design process, and we'll get into some examples tomorrow, but the basic design process is to kind of evaluate the facility to say, okay, well, it looks like this is kind of the happy medium where my most cost-effective project is going to turn my energy curve into this kind of plateau. So you can kind of see the plateau right here where the solar array is coming on and lowering the demand, and then the solar array is coming on and lowering the demand. And then on this partly cloudy day, the solar array doesn't come on quite as much as it should. And here in yellow, we see the battery turn on to make up for it. And so the battery is not being used every single day. Yeah, it's used a little here, it's used a little there just to keep our plateau from spiking. And then maybe 1 out of every 3 days, it comes on during that partly cloudy system to provide a little bit of momentary demand management. And so even in this application, it's not that on a every single day basis where charging the battery and discharging the battery and charging the battery and discharging the battery. In a commercial solar peaker battery, you may not be running the battery every single day. In fact, if you're running the battery every single day, you're further down the mountain. And if you stayed up at the top here, you'd probably get a quicker payback. And so the goal is to turn, a very spiky electric load into something that is more like an even plateau during the day. That's a complement of both your solar production and your battery production. Let me check if I have any questions. So it's definitely worth it to go to your utility website and check out the rate structures that are available. You might surprise yourself and find some residential demand structures. This is an expansion of that graph we saw earlier, where we see markets like Con Edison of New York, or so here's Con Edison at 26 cents, or California at 29 cents. Alaska has very high electricity pricing. Hawaii has very high electricity pricing. But then there's other markets that are a little surprising on this graph, like Iowa. Iowa is not known for having high electricity pricing, but here's a city that does. Kansas is not known for having high electricity pricing, but here's a city that does. Nebraska would be the same way. New Mexico. And if I had to bet, if I went and looked at Kimball, Nebraska, or Independence, Iowa, or wherever this is in Kansas, these would be small electric co-ops in very rural areas. And these would all be, prime markets of where demand charges are very high. In fact, since we're on the topic, let me see if this slide made it real quick. Let me do a quick Google search. So it used to be that this data wasn't collected. When I started teaching this course, actually, the data was not collected. But then National Renewable Energy Labs did a study and identified the markets where maximum demand charges do vary throughout the country. So let me put this link into the chat box. Well, there we go. So this is a graph. It's probably the most valuable chart in the whole solar industry right now, if you accept the premise that commercial peak batteries are the most explosive market because they have the best payback and they have been the smallest market segment historically. So then you go and you look at, well, where are demand charges approaching the $20 to $30 range? And I would say even in the $14 on up is pretty good. Here I am in Mississippi, and the economics of solar look absolutely lousy because we don't have net metering and our residential price of electricity is pretty low. Well, it turns out that Mississippi has pretty high demand charges compared to Louisiana or Texas or Arkansas or even Alabama. So it turns out Mississippi has a untapped commercial solar market that's just ready for development. Here's the east coast of Florida. Florida does not have good net metering, but it has very high demand charges. And little pockets of the United States, like Idaho, has low energy prices, but this part, kind of by, I think that's Idaho Falls, has very high demand charge. I guess there's not much in Utah here, but we can see in Colorado certain mountain ranges. You get up to the top of the mountains and the co-ops have sky high demand charges. So this is actually there's pockets in the middle of the country which have been considered, no man's land for the solar industry because, for better or worse, they don't have good solar policy, and that's, in the simplification is because they can't afford to, where they've relied on high demand charges in order to support the local area. A good telltale sign is that in your developed markets, the commercial electric rate is a little bit cheaper than your residential electric rate. But in these high demand charge areas, because of the demand charges, the average commercial rate is actually higher than the average residential rate. It's all of these markets that are prime for disruption through commercial solar batteries. And it's also those markets where the electric grid could very well collapse on itself overnight, because these commercial businesses in these manufacturing centers have been kind of propping up the electric grid with their revenue. And if they start implementing solar batteries, and on the other hand, the solar customers with really bad solar policies start going off grid, you all of a sudden the whole revenue stream of these what are often monopoly cooperatives evaporates overnight, and the electric grid collapses. And so there's this concept in the solar battery world called the utility death spiral, where utilities all of a sudden see their revenue deplete to the point where they go out of business. And the concern is, oh, everyone in California is so solar crazy, so they're going to see the utility death spiral first. Or hey, New Jersey is well, I guess New Jersey's down here. But New Jersey is over subsidizing the solar industry, and so their utilities are losing revenue, and they're going to go out of business first. Well, it's actually the middle of the U.S. that has these sparsely populated rural electric grids on high demand charges and very poor solar policy, that they're really going to have to figure out what that middle ground is, so that their solar customers, don't just come in, obliterate their revenue and then go off grid potentially. I don't have much to say on the utility scale market. Um, as far as is AC coupling or DC coupling preferred, AC coupling is preferred, and that's for the same reason that we've discussed before. With a grid connected battery, you're not using it all the time. With an off grid battery, you're using it for 3/4 of the day. For a grid connected battery, you're not using it all the time. On a commercial solar peaker battery, you're only using that battery during the peak times when your solar array is not on. So you're only using it maybe 1 out of every 3 days. On a residential grid connected battery, the battery is just hanging out and not really doing much, except during a power outage. So you're not using the battery all the time. On a utility scale battery, it's kind of a hybrid between that residential case and commercial case, where the utility scale battery is doing two things. One, it's helping stabilize the grid so that if there's a power outage on a neighboring grid, when the power blips, it blips the adjacent grids too. And so a battery helps stabilize your regional grid so that power outages that in the past would take out the whole northeastern seaboard don't cascade through systems that would otherwise be unaffected. Now, utility scale batteries may also be deployed in order to reduce congestion on the grid during peak times. And this is a little bit out of my expertise, But what I kind of do to look at this is to look at how utility scale transactions occur. It's actually kind of fascinating how complex grid transactions get. To take a central power plant and push that electricity all the way down to its point of use, it's kind of like a boulder sitting at the top of a mountain, and it needs to roll all the way down the hill to get to the point of use. And if your power plant is really far away from the home, then that power plant has to be larger and larger and larger. Your voltage has to be higher and higher and higher in order to get enough capacity to pass the boulder all the way down the hill and into the valley below. And so when we come out of our power plant into our transmission lines are at extremely high voltage, and then they step down to still extremely high voltage. And then they get onto your regional grids that are at lower voltages. And so by the time you get out to your residential homes, you might be looking at a 25 kilovolt line that then steps down to a 240 volt transformer that feeds your home. And actually, when you get into very rural grids, they actually will not run at 240 volts. They may be running at 245 or even 250 volts, simply because they need to pass more power further out to the end of their distribution circuits. We have a couple of different ways to structure an electric grid. One way to do it is to say, okay, there's one company in charge of everything, like the Tennessee Valley Authority. They may own their power plants. They may contract with outside power plants. They may assign little fiefdoms to say, okay, a grid distributor is in charge of this. And that's what we would call a regulated grid. And it's very easy to set up transactions on a regulated grid. So in one sense, there's less red tape. On another sense, there's less competition. And so, it's like a monarchy, and what the king says goes. And so the counter argument is, on a deregulated grid, you have more competition, and so the consumers get better rate structures accordingly. And I would say that is true. The TVA being an example, the TVA does not provide net metering to a solar customer. And so the instant a solar customer wants to put solar on their home and outflow onto the grid, they get avoided cost for that outflow. And if they were over in Texas, Texas does not have any net metering policy. But if you're in Houston, Texas, and you don't have net metering, you get retail electric providers, you'll get multiple offers to say, hey, solar customer, I'm not going to give you retail price net metering, but I'll give you 70% of retail price. I'll give you 80% of retail price, because I want to sell you the remaining 20% of your electric use, because you're not going to do 100% on most homes. And if a couple customers do 100%, so be it. I'll collect their meter fees, but I want the solar customers who aren't doing 100%, and I'll give them more than avoided costs in order to pick up that business. So in Texas, you have no net metering, but you have competition, and therefore solar customers get a rate that is better than what solar customers get on a regulated grid in the TVA region. And what's funny about the TVA is that they were given this monopoly in order to put power out to the most rural parts of the US, and now they have a solar policy that discourages point of use power generation. And it really should be the other way around. So that's just kind of an anecdote of where we see regulated grid structures not really doing what they were intended to do. That said, on a deregulated grid structure, the electric price transactions can become quite chaotic, and you really need a lot more expertise in order to participate in them. So, to their credit, the TVA does do some utility scale programs. I think it's kind of ridiculous because they pay their utility scale programs more than what they'll pay their own customers for grid intertied solar. So if I'm a utility scale developer, I might get a PPA in the 4 cent or 5 cent range. Whereas if I do a net metered solar array on the TVA region, I only get 2.5 cents for my outflow. Anyway, if I'm in Texas and I have to compete, I have a crazy system where I might go and contract with a power plant over a long-term PPA, but my facility energy use is variable, and the power plant may not be able to vary their output in order to meet my actual facility energy use. So either the facility or the power provider is on the hook for making up those differences. So somebody in that process, usually it's the retail electric provider, is looking at a real-time market for day trading electricity. And so not only do you have long-term contracts, you also have day-ahead options where they look at what the weather should be like in the day ahead, and they guess at how much energy they need to supply their customers. And then there's also a real-time market, and so the energy gets delivered to the customers no matter what. And then they go backwards and say, okay, who's been contracted to who to supply and deliver what amount of electricity, and anyone who comes up short, there's a settlement process where you pay even more money if you sold more electricity than what you contracted to buy. And so if you're interested in learning more about this kind of real-time cost and settlement market, one of the best resources you can do is go to Twitter. So Twitter is vilified for many reasons, but it's also, Twitter is good for real-time, day-to-day information if you know where to look. And so I'm going to plug in Texas's grid, which is called ERCOT. And so here's ERCOT's Twitter account. And here's also people tweeting about ERCOT. And I follow this guy because he kind of puts interesting graphs on Twitter. And, this is what the dashboard of a electricity day trader might look at. And say they look at ERCOT's load going up and going down throughout the day. So here's ERCOT's capacity going up and going down. And I'm not going to get into what all of this stuff means, but let's just look at some comments. Here's one where just for a brief instant of time where power may hit $9,000 per megawatt for a very brief instant of time. So $9,000 a megawatt hour is $9 a kilowatt hour. And so for a very brief instant in time, which I don't really know what all these graphs mean, but maybe this time right here at 7 p.m. in Texas, there's a spike in demand with a very huge shortfall in supply. And so here we have the $900 pricing point for a block of energy at that time. And so if you deliver electricity at 9 p.m. or 7 p.m., whenever this time is, at that time, if you have energy that's available to be delivered and you shove it into the grid and somebody comes up short where they delivered that energy, but they hadn't contracted for the demand, and you're involved in, this kind of complex settlement process, you can say, hey, I'm the one who fulfilled that contract, and so you owe me $900 because you used that energy and didn't have a contract for it. And the deregulated structure lends itself to this. There's still kind of a settlement process that's overseen by ERCOT to make sure that enough power is available for supply and enough power can be delivered. And so that's kind of like what Tesla is doing over in Australia, is installing utility scale batteries that can be discharged maybe just a few times a month during this $9 a kilowatt hour time. And eventually what that should do is make these utility scale batteries cost effective, but also over time smooth out those rates so that we don't see such volatile pricing in deregulated markets. And so I think there's definitely a debate on whether or not a very simplified regulated rate structure, on paper, you don't have the chaos of a deregulated rate structure. And so you should have more streamlined processes and better policy accordingly. At the same time, there are problems with monopolies in that just they don't always make the best economic decisions that might naturally occur with a more deregulated rate structure. And so the other trend is to divide up all of the roles and responsibilities. And so actually in Texas, and I use Texas because they're like the more extreme model where the distributors are not allowed to sell electricity, but the transmission companies are not allowed to be the distributors, and the power generation companies are not allowed to be the transmission companies or distribution companies or the retail electric providers. That's where it's very easy to understand how in Texas there's no net metering, because the retail electric providers, they say, hey, it's not my job to buy electricity from my customers. And the power generation companies say, we're not allowed to be the retail electric provider. There's too much division of scope for a policy of net metering to really be implemented. At the same time, maybe it's overkill. I mean, you get into issues where the grid distributors would really like to go and put batteries on the power lines and distribute batteries. And a distributed battery can provide value to the grid, because what happens during a power outage is, let's say you have a tree fall over these power lines and it kills the power line right here. Well, now all this power trying to flow into the grid can't get there because of the power line, so they isolate that section of the grid and everything goes blank. Well, what also happens when the power line goes out there is now electricity starts flowing to the fault. And electricity on this grid is supposed to be flowing the opposite direction. It's not supposed to be flowing outward. It's supposed to be, or inward. It's supposed to be flowing outward. In fact, with solar, you can have too many homes, and this does not apply to Mississippi, where solar is still less than 1% of the electric grid. But it may apply to cities like Boston or San Francisco or Long Island, where the price of solar or the price of electricity is so high that maybe not in the entire state, but maybe in one specific community, a whole bunch of people have done solar. And so now they're starting to push that electricity the opposite way. And the little transformers on the side of your house can go multiple directions. They can go both ways, but at some point, the utility distribution transformer starts to read, uh-oh, power's going the wrong direction. They see it exactly the same as a power outage on the line. And so when the utility says, oh, if we have too much solar on a distribution circuit, it can cause our system to go haywire, that's absolutely true. It's a matter of system upgrading. And so then if you have to upgrade the distribution system, it becomes a question of, well, does everybody pay for it or do the solar customers pay for it? And that's a matter of debate. So back to batteries, the distributors, one solution for this would be to put batteries, either at the residential transformers or certainly at the distribution transformers. You could start putting batteries there. And that way, when part of the grid goes down, let's say a tree falls over this power line and it takes the grid down there, and it takes the grid down there, and it takes the grid down there, and the grid down here. But this little solar community, as long as they have their solar arrays and the utilities put a battery at the distribution point at the substation, this community can remain online as the rest of the power infrastructure gets fixed. Yeah, I was reading about Katrina in Mississippi, and it was like 3/4 of Mississippi lost power during Katrina. And some customers that were way out on the rural grid, and we're talking about customers who were 2 hours inland, they lost customers for power for weeks, over a month without power. And while that sounds like kind of like something that might happen in Mississippi, I mean in New Jersey during Hurricane Sandy, right across the street from New York City, there are customers who lost power for weeks as well. That's just the thing about disasters is there's only so much preparation you can do. Now, Houston, Texas, with Harvey, did not see the power outages of Katrina and of Sandy, and that was largely due to the fact that before Katrina, Houston had the largest disaster, which was Hurricane Allison, which had happened just a couple of years earlier, and so they had, or Tropical Storm Allison, but it still caused billions of dollars of damage. And they upgraded the grid at that time, and they put a lot of their power centers above the floodplain. And so they didn't have the, in Harvey, they actually had to go and turn the power off during the rescue operations because they had built their grid to be so resilient. So, there is some planning you can do through grid upgrades. It's just a matter of who pays for it. Kind of bringing the discussion back home, in Texas now, some distribution companies, they say, well, we want to upgrade our substations and put batteries on our substations. Well, then it becomes, well, who owns them? Because the distribution companies and the transmission companies are not allowed to be the power generating companies. And even though they're not technically generating the power, they're just storing it. Batteries are treated as power generation devices. So there can be kind of an over application of deregulated electric grids that kind of stymies the development of batteries. At the same time, it can be hard to make the horse drink the water if you even if you lead it to them. if you have a monopoly that just does not want to do distributed generation. And I've been kind of ragging on the TVA a lot, but you go into the published reports by the TVA and their 2018 rate case, they say we don't do distributed generation because it raises the price on non-participants. In page one of their executive summary discussing their rates changes. And so, whether or not they're being fully analytical about that or just trying to maintain the status quo, either way, they're saying, look, we're going to be very anti-solar as far as consumer-owned solar goes. And so in that kind of entrenchment, it can be hard for you to get your, what you want to do with on-site power generation pushed out. So what we're going to do tomorrow is we're going to talk about different battery types. We're gonna spend a decent amount of time talking about the differences between lead acid batteries and lithium ion batteries. The short of it is that you want to use lithium ion batteries for batteries that are only running for 1 to 2 hours. And so if you have a commercial building and you want to do demand management and you look at the load profile and you realize that you only need the batteries for 2 hours at a time rather than 5 hours at a time, at that point, lithium ion may make sense. Otherwise, lead acid still offers a lot of value. So for your off-grid customers that are running off batteries for 3/4 of the day, lead acid is going to be the way to go, whereas lithium ion is still kind of a niche specialty. So we're going to talk about those batteries and the different types and costs and how to read battery spec sheets kind of for the first half of the program. And we're going to get into calculating the levelized cost of storage based off reading battery spec sheets. Then we're going to get into an off-grid design exercise where we go through a customer's monthly electric bill and run a PV watts calculation to determine how large of a solar array they need, how large of a battery array they need based off their energy use. We're going to talk about, the brass tacks of system selection on, do you need one inverter or two inverters? We're going to talk about the spacing requirements. We're also going to show you how to make a chart that looks like this, which is a hour by hour graph of the state of charge of the battery bank itself based on solar production and facility consumption. So this is for off-grid sizing to answer how large of a battery bank do you need. So a lot of spec sheet reading and some modeling and some code discussion that should assist you with your battery bank layout. Using a real case study that I've done locally where the customer has been living in his off-grid actual house, so not like a yurt, but a real house with a wife and 2 kids at home and school. Not the kind of customer who wants to run out of electricity. So we'll look at the project logistics and what we did in that project to make it a nice kind of off-grid array, including budgets and material lists. So it's going to be a big full day tomorrow. We'll be looking at spec sheets and not just data sheets, but kind of the odds and ends of off-grid design on what accessories you need to make the systems work well. Then we'll also spend some time looking at lithium ion and the Tesla Powerwall and some of its performance specs, because of course that's what everyone's going to be interested in. Wiring diagrams, kind of some pitfalls to look out for. and then kind of do another case study that's not for off grid, but that's more on how we prepare a job site that they don't have the budget for batteries at this time. What do we need to consider for preparing that job site for a battery upgrade on into the future? And then at the very end of the day, we're going to come back to the commercial market and look at some sizing software and show you, how you kind of develop